So, are there any questions about Lab 1? Lab 1 you should demo out this Thursday or Friday. Demo for Lab 1 is not very arduous, but you should show the TA the stuff is working, yes?
Actually, there's one question. My group really checked off last week.
Uh-huh.
We recently sent out that correction of how to do with the offset, and we used it.
Don't worry about it. The correction on how to deal with the offset is as much for my information as it is for yours.
So it's not a huge deal.
It's not a huge deal. It's one of these things where I might have known that a year ago, but I didn't know it this year until Akshay found it online. And makes total sense. There's a parameter you can set. The default, I'm not even sure why the default is differential. So you can do one of two things. One is you find out which other lead is the negative input lead and ground it. That'll work. Alternatively, set the mode to single-ended, and that'll fix it. Or you can go in and hack the device directly, which is what the National Instruments documentation showed. Any other questions about Lab 1? Let's start talking about Lab 2. Lab 2 is kind of an instrumentation warm-up, finger plethysmograph. And in a finger plethysmograph or a pulse plethysmograph, what you're going to be doing is to take a infrared LED and shine light through your finger to a phototransistor. And so there's light going through your HNU. And the opacity of your finger changes with the amount of blood. There's various technical details in this which make it interesting. One is the LEDs we're using and the phototransistors we're using are very, very directional. And so you're going to get best performance if they're pointed right at each other, or if they're side by side and pointing in the same direction so that light scattered back here is scattered back into the receiver. It works both ways. I think with the brain reading infrared device you guys built, you could actually see the pulse on the scalp as well as brain related stuff. I suggest doing the transmission version of this. The input stage is written as a photoemitter to ground, and then a transistor, an NPN transistor with no base connection, which is the infrared receiver, going up to a 20K resistor. I originally put a 100 ohm resistor in here. Don't use 100 ohms. Use 300. If you need a little more signal to noise ratio, go down to 100, but it draws a lot of current, like 150 mils with 100 ohms. It's brighter, the LED will take it, but there's no particular reason to go that bright. And there is a slight, all right, how much infrared can you put through your skin and not hurt yourself? The US guidelines say that you must limit the intensity to 1/10 of sunlight. Sunlight, most people consider what sunlight is generally recognized as safe. It's a radiation exposure. It sunburns you. You can cook yourself with it if you manage to get the reflectors just right. But sunlight is generally recognized as safe. Typically, energy exposure to your skin has to be limited to 1/10 of sunlight level. Sunlight is a kilowatt per square meter. That works out to 100 milliwatts per square centimeter. So if you're shining this LED through a few millimeters of skin, you should probably limit it to a few milliwatts. Now, is it going to matter if you heat your finger a little bit? Probably not. It probably matters more if you have this thing pointing into your eyeball. Your eyeball is probably the most temperature sensitive piece of your anatomy. Guys that used to work on the dew line radars, distant early warning radars in Alaska, these are 10 megawatt radars, right? To get warm, they'd stand in front of the antennas, which worked. They developed two problems. Number one, they developed cataracts. Number two, they were sterile. The sterility was reversible because it was heat-induced. The cataracts were not. Your eyes and your testes, if you have them, have remarkably poor blood flow, and so they don't tolerate energy input very well. Limit the current here. I don't think there's a safety problem, but turn the current down. If it doesn't work, then turn it up, but it should work. So the current generated, the state of this transistor is on when the infrared is seen, which means that bright infrared drops the voltage here. So what you're going to see coming out of here with heartbeat is, oh, maybe 1.5 volts or so, something of the sort, maybe 5 volts, with a little tiny signal on it corresponding to the heart rate. I'm exaggerating that so you can see it on the board. The change in intensity is parts per thousand. Okay? We want to amplify this, but of course, with a 1.5 volt offset, the very first thing we have to do is get rid of the 1.5 volt offset, or when we multiply it by 100, we're going to get 100 volts out of the op-amp, and that's not going to happen. All you'll get is a saturated op-amp. So the very first thing that's got to happen to this signal is that we're going to have to put it through a high-pass filter to strip off the DC. High-pass filter, Bode plots. Log frequency. So on a log frequency scale, 0 frequency is way down there, right? It's negative infinity. And the cutoff, or the frequency response, is going to look like this, where the break point here is 1 over RC radians per second. So no matter what capacitor you put here, DC is going to be completely removed because it's infinitely far away on a log scale, so the response is 0. That's another way of saying capacitors block DC. Then we're going to put this signal into an op-amp that is configured for a gain of about 100. It's actually 101 because we're going to use a 1K resistor and 100K in the feedback loop. Non-inverting configuration, gain of 100. And we're going to add a capacitor across the feedback loop, which turns this almost into a low-pass filter. It's not quite, but it's very close. So that the net response coming out of, so let's call this R1, C1, R2, C2. The net response coming out of this stage is going to be something that looks like this. That's horrible. Let me draw that again. Log frequency, log amplitude. This is 1 over R1, C1. This point is 1 over R2, C2. The reason I say this is approximately a low-pass filter is that the gain actually levels off at high frequencies due to the non-inverting configuration here, but it's a very small, it levels off 2 orders of magnitude down in amplitude, and so you can't detect it. So, what frequency should this be for heartbeat? What should the low frequency cutoff be? Your heart rate is periodic with a frequency of about 1 hertz or so. So call it 6 radians per second. So where should you place this cutoff to get rid of DC and allow this signal amazingly loud?
But it's less than that. It's less than 1 hertz.
Well, it depends on the person. If you're in shape, you might be down at 50 beats per minute.
Down to 40 something.
Really? 40 beats? So you work out a lot. 40 beats. The lowest, I used to run with a guy who's...
43 for
for-
my last one.
Very nice. I used to run with a guy whose basic heart rate was about 32. When he was working really, really hard, you know, producing half a horsepower, his heart rate was up to my resting rate, which is about 60.
So you should probably do like half hertz.
Yeah, so, I mean, you tune it for your heart rate, but yeah, you might have to go to, you might want to tune it to 2 seconds here. So the low frequency cutoff, if you want to adequately represent this waveform, you're going to have to pass frequencies down to something like a half a hertz, or about 3 radians per second. This is saying that 2 pi is equal to 6, right? You know? Close enough. About 3 radians per second. And how about on the high end? What should you be passing on the high end? Well, so now thinking in Fourier terms, this waveform looks something like a sawtooth, right? It sort of goes up quickly and then down slowly and then up quickly and down slowly. And you could look up the Fourier transform of a sawtooth. But more or less, it's going to be true that you have to have a frequency, you have to pass a frequency which is high enough to capture 1 cycle of the sine wave that fits the rising phase. Right? You believe it? Okay. So you're going to have to look at the width of this, and this waveform rises in 100 milliseconds or so. So you would guess that you're going to need a time constant which will pass something a little bit higher than 10 radians per second. So call it 20 or 30 radians per second. So I don't know, call it 30 radians per second. Maybe a little more. Maybe go as high as 100 radians per second. But it brings up an interesting question: why put a cutoff here at all? 60 hertz noise. 60 hertz is everywhere. the field, as I've probably said in this class, I can't remember now because I say it in almost every class, if I put my hand up like this towards the fluorescent light, the field across my body is probably 250 volts. The current is very small, so I don't feel it. But there's a skin current of a few hundred nanoamps back and forth between my feet and my hand. And that very large electric field, which is caused by the fluorescent lights and by the plugs and by the power line going to your laptop and by everything in the room, can induce can be capacitively coupled into this wire. Now this capacitor is one you didn't build. It's there because of the geometry of your body, but couples you up to the fluorescent lights. And you may find that you get 60 hertz induced in. You might not if you're very careful about construction. If the breadboard that you're using, the solderless breadboard, happens to be on an aluminum substrate which you ground, then you may find you don't have noise problems. It just depends on the geometry. If you ground yourself while you're doing this, you may find you don't have any noise. But if you ground yourself, you better be darn sure you don't accidentally touch a 110 volt line, because you will die. So I don't recommend grounding yourself actually in this class. So you would like to choose this cutoff point so that it's high compared to the periodicity of the waveform, to the rise time of the waveform, but it's low compared to 60 hertz, which is 360 radians per second. So the filter will be very low amplitude by the time it gets out to 360 radians per second, right? So the first time I built this, I used the recommended values that I found on the web, like everybody does. 20K and 10 microfarads here for the high pass. You calculate that out. So it's 5 times 10 to the minus 5 times 2 to the, I'm sorry, 10 just 10 to the minus 5 times 2 times 10 to the 4 looks like to me about 0.2 radians per second. I'm sorry, 0.2 seconds, which is 5 radians per second. So it's a little too fast, really. You ought to use a bigger capacitor or a bigger resistor there. This is just on the that's as small an RC product as you'd want to have. You probably want a bigger one. The recommended size on the other side was 100K and 0.5 microfarads. So we have 5 times 10 to the minus 7 times 10 to the 5th gives us 0.005 seconds. Is that right? Which is 200 radians per second, which seems a little high. No, wait a minute. 0.05. 20 radians per second. Ooh, that's marginal. It probably should be smaller than that. So you might want to go to 2 times 10 to the minus 7 farads equal to C2 rather than 5. Point is, play with it. These aren't cast in stone. If you were to make the cutoff here too high, you're going to start seeing things that look like this. You're going to get a very large distortion of the waveform. If you make the high cutoff too low, then you're going to start to see a degradation in the rising phase, so you're going to tend to be more averaged. You're going to get attenuation. So an experimental way to do this is to start with these lines fairly close together and then move them out until the waveform doesn't change shape very much. And then you probably have all of the energy. Turns out a gain of 100 may be enough for some people under some circumstances. If you have very warm hands with blood vessels close to the surface, a gain of 100 may give you a big enough signal. But probably you're going to need another gain of 100 to make it work. And so what I'm going to suggest doing, I don't want to run this to ground right now. The original circuit for this has VCC has the positive supply of the op-amp at 5, the negative supply at ground at 0 volts. To make this work well, we need to have a reference voltage on the op-amp which is not exactly ground, and the easiest way to generate it is to run this to ground, but run from +5 again, run a resistor and then 2 diodes in series to ground, and then treat this as the reference voltage for the op-amps. Each one of these diodes drops about 0.7 volts, so this rail right here should be about 1.4 volt. So that becomes our 0 reference. Doesn't matter because everything is AC coupled. We're going to use a 3-terminal resistor, a so-called potentiometer, here as a gain control. And then build the same circuit again. Build the same circuit again, and then run this into the USB 6008, the National Instruments NIDAC. Because each of these stages has a gain of about 100, the overall gain is 1,000, but it is variable from 100 to 1,000 to 10,000 because of this trim pot. So you'll adjust this up and down until you see a good waveform. What does good mean in this context? Well, the A to D converter is set to ±5 volts, and it is a 12-bit A to D converter. That means that it can recognize 4,096 different voltage levels. So it goes ±5 volts for 4,096 voltage steps. So it's 4,000 voltage steps scattered over 10 volts. So if the amplitude of your waveform is 1 volt high, then you have a resolution of about 400 counts, or about a quarter of a percent. If the amplitude of your waveform is 100 millivolts high, then you have about 40 counts effective resolution, and you cannot possibly under any circumstance do better than 2.5% accuracy. Therefore, if you want reasonable accuracy, let's say 1% accuracy, you're going to have a waveform which is something like half a volt to a volt high at the output of this point. So the peak-to-peak measurement here should be 0.5 to 2 volts or so. And you'll adjust the gain until you get that. So, any questions about this? It's a straightforward instrumentation problem, but it implements a bunch of interesting stuff. There's high pass filters. There's 2 high pass filters, 2 low pass filters, 2 gain stages. It's a little bit noise sensitive, but not ridiculously noise sensitive. So it's a little bit of a challenge to get it working right. There's enough to play with to make it interesting. What happens if you just pull this capacitor? Is the noise overwhelming, or does it still work? What happens if you try and DC couple it? Yes? Yes, I know.
Let's see how much he's going to owe me.
You better, yeah, take it out, take it for a drive before you give it back. Bend a fender. So, play with this thing. It's not a hard instrumentation job to set up, but there's enough here to mess with. Akshay?
Can you go over why you have to put the diode in?
Right. So an op-amp can't possibly produce a voltage more negative than its negative supply, which means that if we want this thing to have gain all the time, because part of the time this voltage is going to be more negative than this voltage, we have to bump this voltage up above ground. The alternative is we use ground here and we make this -5. Either way will work.
Why do we have negative voltage now? Like we just had it going
For full
to 0
swing.
So let's say, since this is AC coupled, part of the time, if this voltage is trending positive, you're going to be injecting current here. This voltage will go positive. If this voltage is trending negative, then current will be pulled out of here, and this point will go negative with respect to this. So there will be a negative voltage with respect to this terminal.
What's the voltage turning negative?
Let's say this is, it's getting brighter here. Or, yeah, the light's getting brighter. It's pulling this voltage down. Another way of saying it is that for an op-amp with negative feedback, there's the two golden rules of op-amps. We're going to go through this a little more. One is, if there's negative feedback, the positive and the negative terminal should always have the same voltage. And 2, no current flows into either terminal. Right? You all remember this from someplace, 2100 or instrumentation or something. Right? And if current is, if this point, under some circumstances, this can pull negative, and this point has to be biased high enough that it can respond to that point going negative by dropping the output voltage. So you can wire it two ways. You put the diodes here and ground this, or you make this ±5 and ground this. Either way will work. But don't take my word for it. You can't hurt this circuit. Ground this point and watch what happens to the output. All right? That's the best thing to do. And you'll find that it's clipped. So you'll see something like this. There's going to be a separate circuit which I'm going to ask you to build, which records your breath, which is going to be just a piece of hookup wire around your chest with a little piece of stretchy material. So the stretchy material is going to be modeled as a variable resistor. And what I suggest doing is putting a fixed resistor of about the same resistance in series with it, driving it off of 5 volts, and putting this point directly into the NIDAC. You should get a nice big signal. So you measure this, you hook this around your chest, you measure its resistance. Make this resistance about the same size. And then as you breathe, this resistance will vary, which will cause this voltage to vary, which is easily detectable by the NIDAC. So there'll be 2 channels of input. Channel 0 can be this guy, and channel 1 can be this guy. However you want to work it out. Oh, yes. Confusingly, both these devices have 2 leads. The long lead on the LED is the positive lead. The long lead on the phototransistor is the negative lead. Don't ask me. These are all in one drawer. You could tell them apart because the transistor is black. Because the molded into the body of the plastic is a bandpass filter, an optical bandpass filter that filters out visible light and only allows infrared through the body of the transistor. That helps quite considerably with noise caused by the room lights. Otherwise, if the transistor saw these lights, it would be flickering at 120 hertz at full volume, and it would be just a very loud, annoying optical signal. As it is, these transistors barely can see the lights in the room. They can see the sun, though, because the sun has quite a lot of infrared output. So if you find yourself on the rare occasion that sunlight actually comes into 238, if you happen to be sitting in the sun, this probably won't work. Let's close the curtains. Keep your complexion pasty pale. One of the technical aspects of this lab is I'm going to ask you to, part of what you're going to hand in is video, is a recording, a video file of your pulse being recorded by MATLAB. And MATLAB has the ability to auto store animation frames to an animation file. So I'm going to ask you to do that. Rather than hold your phone camera up and try and get some cheesy picture of the screen, I'm going to ask you to directly grab the frames with GetFrame and then append them to a video file so that we can watch your data turn from bad data to good data and then scroll across the screen this way. So we want a scrolling display, and we want a video of that for the TA to be amused by. Another aspect is that we want you to do some signal processing and determine when the waveform is periodic and when it isn't. Has anybody thought about, I've mentioned this once or twice before, but has anybody thought about how they're going to do that? So part of the time, you're going to be moving your finger in this gap, or you're going to be settling your hand down. And by the way, what I suggest doing is resting your hand on the table so you don't twitch too much. May avoid the coffee too. Yes?
Something to just consider, but let's say you have like a consistent where you're looking at trying to find a peak, right?
Uh-huh.
And then let's say you find peak 0, right? And you find the next peak, and you calculate the time between that, and and then you find the third peak, and you see that time is the same as the first time within some tolerance. And if it is, then it's periodic. If it's not, then it's not periodic. And then you look at the, you sort of repeat that process.
All right, so that is a perfectly valid algorithm that would do what I'm asking. So what you're saying is look for consistency in the period. And that is a perfectly valid way to do it. I would say that there are a couple of technical things about that you might want to change. Rather than detecting the peak, you might want to look at the crossing of the average. So you take the long-term average of this waveform, let's say over 10 beats, and that's going to, if you do this on the fly, if you do this, you don't have a calibration period and then just let it be unchanged, but you calculate the mean continuously based on the last 3 seconds data or 5 seconds data, then the mean will always fall on the waveform. And the mean will be about, given this is a fairly asymmetric waveform, it'll be probably 1/3 of the way from the minimum to the maximum. Something of that sort. So you could use the mean or some multiple of the mean, ask when the waveform crosses that. The next time it crosses it, you know you've gone one cycle. That's a little more robust than the peak because the derivative is higher here, which means your time estimate is better. You know better, when you have a steep line, you know better when it crosses a fixed amplitude than when you have a flat line near the peak. Oh yeah, you'll have to do that. So you'll have to say it passed the threshold and the slope was positive.
Well, can't you just take every other threshold? Because take the first threshold and the threshold after the next must be the same thing, right? Because you assume you go up and down.
Yeah, so I think you could do that. And if you got out of phase, it would still work. If you missed one someplace, it would still work. Did you have your hand up?
Yeah, you might be able to fit a line to the points around that threshold and then calculate where that line crosses.
That is a, okay, now what you're suggesting is in the presence of noise,
Right.
in the presence of noise, if you have some threshold line, a more robust, yes, a much more robust thing is to take the 5 nearest points, fit a straight line, and then calculate the exact crossing. And you're quite right, that is much better and more reliable. You could also do a higher order thing. You could say, I believe I'm going to take the first 3 Fourier components of this thing, plot those, and those, after all, the first 3 Fourier components are an averaged version of the waveform, and then fit that. Or you could do a cubic spline. There's lots of different ways, but probably a straight line fit is good enough. That will help the signal to noise quite considerably. So there's a basic trade-off now. As you said, the minimum you have to do is compare 2 periods to see if you have a consistent period. If you were to compare more periods, you would have the chance of, you could say with higher confidence that you have a periodic waveform. But the response speed goes down. If, let's say, you have to wait 10 periods before you say, aha, I've got a heartbeat. Now you're talking about 10, 15 seconds, depending on your heart rate, before you can say it's valid data. On the other hand, if you only wait 2 periods, you could say it within a second or 2, but you might be wrong. So how long should you wait?
I feel like it depends on your sample, like Well, I guess I guess it doesn't suit the heartbeat that it's changed.
It doesn't. Well, it depends a little on your sampling rate. If you're sampling very slowly, then you will have a problem. But if you're sampling at, say, 30 times a second, then you over 1 second you'd have a maximum of 3% error, and your natural heart rate varies that much. So one possibility would be to make the trade-off explicit. One way to say would be average over 2 periods, and now I have a heart rate of 56 plus or minus 10, and but when I average over 10 periods, I have 56 plus or minus 2, because the standard error of the mean decreases as you increase the sample size. So one way to do this would just be to make the trade-off explicit. Give a heartbeat and the error range, which would be the variance of the number of beats you have in the sample up to some maximum. Has anybody ever seen a pulse meter that did that? I've never have. I think there's a good reason for that too. Most people understand a mean. Most people are not very comfortable with a variance. So, but that's a possibility. Another way is to just make an arbitrary cutoff and say, if the variance goes below 10% of the mean, I'm going to call it valid. Pick the percentage, right? So we're going to give a yes, no, green light, red light, based upon whether the variance is below some fraction of the mean. This is all time domain, right? This is all thinking about periods, which is perfectly valid. The other way to do it, of course, is frequency domain. Take the signal, Fourier transform it. You need a resolution now of 1/10 of a hertz or so, because you want to get the heart rate within 10% at least. It's a one period is a second. So to get a 10% change, you're going to have to be able to resolve a 1/10 of a hertz, which means taking a FFT over 10 seconds minimum. So you could do a running FFT. And again, now what would you do? What would be the algorithm for an FFT? Who'd like to hallucinate an algorithm for fast Fourier transform? Oh yeah, you say FFT. Or if you want to be a little more sophisticated, you say P Welsh, which is a much better estimate than the FFT, because it's been smoothed and averaged for you and all kinds of stuff. But so let's say you took the power spectrum of this signal. Well, clearly there's going to be a fairly big peak at around 1 hertz. If you have a heartbeat of 60 per minute, there's going to be a big peak at around 1 hertz. There's probably going to be some harmonics in here, so you're going to see some smaller peaks at 2 and 3 and 4 times the heart rate. But let's say that you're moving your finger around and there's some noise superimposed upon this signal. Then what's going to happen to the Fourier transform? So you're going to have, we have now white noise with a heart rate imposed on it. And if you transform that, what would happen to the spectrum? It would flatten out. It would become more uniform. So these divots here, so instead of having a nice peak like this, you might have a peak that looks like that, but it would be more, the power would be more uniform over the whole frequency. So what kind of an algorithm could you use then to detect periodicity?
Is there some sort of like minimum amplitude required to know that you would have periodicity? So for instance, if you just look at that eyeballing, right, you have a huge peak there. Oh, it's a peak. That's probably a frequency of that in the actual sigma, right? So could you say find the max of this data point, see what the value of that maximum, that maximum value is, and then find where the frequency of that, and say, okay, since that's like greater than 5, it must be periodic.
So you're saying that the energy has to be concentrated. Yeah, and that's true. It has to be concentrated at a given frequency. Whatever the frequency is, it has to be concentrated. So, but you need something else, I think, besides the absolute amplitude, unless you happen to know the absolute amplitude of the signal, and that's the background level. So what probably matters here is the ratio of the peak to the background.
So the ratio of the max and
The max and the min, right, yeah, exactly. And if you did that, and you chose the correct ratio, whatever it is, I don't know what it should be, then you could probably do this in the frequency domain, and there might be a better way to do this. You might be able to say that the ratio of these two peaks has to be a certain value or something of the sort. But it's going to be ratios of peak amplitudes, something like that. Yes?
But you have the same kind of delay during the display because if you're doing the Fourier transform as the points come in, you still have to wait for like, 2 whole.
You're quite right.
Same time.
You're quite right. There is going to be the same delay because there is just no substitute for a sample length. You have to have the data before you can resolve the frequency. And you're quite right. You're going to have to wait 10 seconds. Regardless, if you want a certain level of accuracy, you're going to have to wait the same length of time whether you Fourier transform or do it in the time domain. And I've been trying to, one of the things I do when I go to doctor's offices is if they slap a pulse ox on me, I count and find out how long it takes to get a valid reading on the pulse ox. And it's a few seconds. It's more than 5 seconds. Now, they may be using a pretty good algorithm, but it's still a few seconds. Question? Comment?
just curious, what is the average heart rate of a human being?
Average heart rate of say a young, healthy human being would probably be around 72, 70, 72.
Goes up.
Pardon me?
If you're unhealthy, it probably goes up, right?
Typically, if you're out of shape, it goes up. If you're stressed, it goes up. If you're too warm, it probably goes up. What can cause it to go low? Well, an AV block. Let's say that your atrium is beating at 60 a minute, but you have an atrioventricle block such that the ventricle is not pumping very well. You might get 2-to-1 locking. So your atrium is beating at 60 and your ventricle is beating at 30. That's not good, folks. But you can survive it. And you occasionally see people that have an AV block of that sort. 72 beats per minute, yeah, more or less. You can also do, well, this brings up an interesting point, though. You can also do rationality checks, range checks on the data to make sure that it makes any sense. If you do an initial estimate of the heart rate and it's 250, you better say, well, it's probably not valid, right? And you might be able to get that if you have the caffeine shakes and you're putting your finger into that thing. You might be able to get 5 a second out of it, so you'd get maybe 300 a minute. So you have to. So if you get something which is outside the range of 30 to 180, I'd say that you're probably not getting heart rate data. You're getting something else. 30 to 180 a minute. Most of you should not be above 100 unless you've just run down the hall. And in the past, I've asked people to do that and to sprint up and down the hall a couple of times, come back in, put their finger in the meter. But you all should be right around probably in the 70s and 80s, I would guess, unless you work out, and you could be as low as 30 or 35, 40. How many? I'm sitting right now, what am I? Just over 60, more or less. Anybody run much lower than 60 besides Nini, the jock? Anybody below 60? Anybody above 80? Resting? Probably not. So I would do some consistency checks also to make sure that you're probably that you're not only are you measuring physiological data, but it's heart. Now, interestingly, the amplitude of this wave does change as you breathe. I think I mentioned this once before too. Your intrathoracic pressure determines the stroke volume of your heart. If you inhale, so that the intrathoracic pressure goes down, the stroke volume increases, you tend to get a bigger waveform. You can shut this off completely if you grunt. You should probably try that. You should mess with it. But you may be able to get the breathing waveform directly from the heart data, and it would be extra cool. You're going to have a chest sensor on you. It'd be extra cool to correlate the chest sensor with the heart data and see if you can extract the signal from the heart data. So on the MATLAB side then, there's going to be a GUI which records the waveform and scrolls it. There's going to be a indicator for good, bad heart rate data. And then if the result is good, there's going to be a number on the screen which is the rate in beats per minute. And then also associated with this will be the much slower breathing signal. Does anybody have any idea how fast they breathe? This is a really hard thing to estimate because as soon as you think about it, it changes. Unlike your heartbeat. Most people can't control their heartbeat. Can anybody here control their heartbeat? Can any of you change your heart rate on demand? Some people can. Not very many, though.
If you have anxiety issues, yeah.
If you have anxiety issues, I mean, that's not exactly conscious control, although you can fake conscious control by thinking of something disturbing, right?
Yeah, you can set up the trigger.
Right, you can set up the trigger. Pardon me?
If you change the way you're breathing, you can affect your heart rate.
If you change the way you're breathing, you can. Yeah. Okay, so if you're quite right. If you change your breathing rate, you can change your heart rate to some extent. Most people can't change their heart rate, though, resting. Most people can. Almost everybody can change their breathing rate. But it's a few a minute. Usually, typically, depending on your vital. How many? 5? 25 is 25 I would say is reasonable for an infant, which is probably where you're getting that number from. But I think that's high for an adult.
Yeah.
No, infants breathe like 60 breaths per minute.
One a second?
60 breaths per minute, yeah. 25 is roughly good for adults. But one with people.
One every 3
I think
seconds.
like what, 16 or 17 is good for adults?
Well, this will be interesting. We can get some statistics on that. But again, you have to do it when you're not thinking about it. Yeah. Was it stand on a corner and don't think about an elephant?
If you're sleeping, you tie around your sleep.
Right, although that sleeping actually changes your breathing rate, and so does dreaming. But so there's plenty to do on this, and I would say that probably half the work is going to be in the MATLAB. Is just getting the analysis so it's nice and stable and looks good and gives a stable scrolling display and where the data analysis is stable. And what do I mean by stable? I guess what I mean is that if you were to look at the data by eye on the screen and estimate that you have a periodic signal here, then the system should also say you have good data automatically. Anything else? I'll add one. You can build a separate channel here. Now, let's say you want to get the oxygen level in the blood too. We're going to do that next time around. Let's say you want to do the oxygen level in the blood. Then you can not only measure you have to measure the hemoglobin absorbency at 2 frequencies. Typically 730 nanometers and 850 to 900 nanometers. You measure the absorbency at 2 frequencies. You can get the percentage of oxygen in the blood. Somebody wants to do that, we could probably come up with the appropriate LEDs, or maybe that'll make a good final project, or the start of a final project anyway. So now, a slightly more general question, and that is, how many people feel really up to speed on op-amp design? Or shall we do a little bit of review on that? I was intending to do that. And talk about the basics of op-amp stuff a little bit. That's not too boring? Okay. I'll do that. If you want to mess with this circuit, you can. For instance, both op-amps may not be necessary. What happens if you try and set up an op-amp with a gain of 10,000?
You can't apply more than that energy per gain, right?
So
Also, just out of curiosity, can you put a trim pot on one of the resistors? So you mentioned that we have 2 op-amps to get variable gain, right?
uh-huh.
Can you just have one op-amp put a trim pot on one of the resistors and you just change that resistor?
Yes, you can. So let's try and draw that out. We would still need to get rid of all of the DC coming in because otherwise it would saturate. And we would still want to have a low pass characteristic here, but we'll hold off on that for a minute. So let's say that perhaps a reasonable upper limit for this resistor would be 1 mega ohm, for reasons I'll talk about in a minute. So this resistor has to be 10,000 times less, which is 100 ohms. So there's 2 things we have to worry about here to figure out whether or not this is stable. The first is the gain bandwidth product of the op-amp. Oh my God, what is that? If we look at the Bode plot of an op-amp, and now this circuit looks like this. We're going to have plus input going to a sine wave generator, negative input going to ground, and we're looking at the output. No feedback. Open loop. The op-amp looks like this. It has an open loop gain. This one has an open loop gain of about 10 to the 6th, about 1 million. It has a cutoff frequency of about 10 radians a second. so 1.5 hertz. And it passes unity gain. This is a log, so this is log amplitude and this is log frequency. And it passes unity gain at about 500 kHz, half a megahertz. These are the parameters for LM358. We use LM358s because they're cheap. So you can build them into stuff, you can blow them up, you can walk on them in the lab, doesn't matter. 40 cents each or something. Say again?
So if I remember this correctly, after 500 kHz, it starts decreasing the amplitude of the incoming signal, right?
That's right. And in fact, it only reproduces at full gain up to about a hertz. And then it starts to drop off. So let's say that you're asking this device to put out a gain of 10,000. Now we can go across to the 10,000 level. Let's say this is 10 to the 4th. Gain of 10,000. We bounce out here. We go down. We can't possibly do better than this bandwidth because there's no gain left in the op-amp. So the 500 kilohertz here is referred to as the gain bandwidth, WIDTH, gain bandwidth product, because we have a straight line approximately, which is trading off gain for bandwidth. So we can say that if we need a gain of 10,000, our frequency is going to be lower than 500 kilohertz by a factor of 10,000. So instead of 500 kilohertz, we're going to have 50 hertz. Well, that's good enough. So the gain bandwidth product says that the gain of this, the maximum gain, or the maximum frequency rather, is about 50 hertz. We may not even need a low-pass filter. The op-amp has become the low-pass filter. The second problem is a little more subtle. The gain bandwidth product is a feature of the op-amp. You can get op-amps that have gain bandwidth products as high as you like, at least up to a gigahertz. So that's not really a technological limitation. This op-amp happens to be good enough for this purpose at this gain. What's more of a problem is that physically, now we have this little package. It's got 8 leads on it. Lead 1 is the output. Lead 2 is the negative input. Lead 3 is the positive input. And these are fairly close together. They're fairly close. These are only 2/10 of an inch apart. Let's say you were to take a wire off of the positive input, this node right here, and just run it close to the output. Now we have a spurious capacitance coupling these two. With a high gain, that means we have, for a little tiny voltage change here, we have a huge voltage change over here in phase. Uh-oh. We feed that back a little bit, and it oscillates.
So you're running the positive wire close to the output wire?
Yeah, if you just run it close by accident, if you don't shield it, it may oscillate.
So that's just running like a copper wire without the outer cover there?
No, it doesn't matter if it has outer covering or not, because this is electrostatic.
Okay.
It just has to be close. And the higher the gain, the more sensitive the system is, until you can't build it anymore. And so, I don't know, I haven't tried this with this particular op-amp. It may not be possible to build this on a whiteboard. Because on a whiteboard, as you may know, there are little pieces of metal sticking underneath the whiteboard which connects all of the holes so you can wire stuff together. And the capacitance between holes is on the order of 10 to 20 picofarads. And so there's automatically a coupling between the input and the output, whether you like it or not. And it may well oscillate. And it's a really quick experiment. Build this up, ground the input through some small resistor. Don't even hook anything here. And if you see a big square wave coming out of here at like 250 kilohertz or so, you'll know that the gain is too high. The thing will start oscillating because a little bit of noise on the input will cause, will feedback positively to make a bigger input, which will make a bigger output, which will make a bigger input until it saturates, until you get square waves that are going from VCC to ground. That could be fun to try. If it works, though, you can do it in one stage. So what resistor would you like to make variable then for the gain here? So
Alternately shouldn't matter. It depends on your trim pot you use. I forget. It's like one.
so it's 1 over R2 over R1, right? Where this is R2 over R1.
And ideally, I want to make R2 variable.
Well, if you made R2 variable, then the gain would be almost proportional to R2. If you made R1 variable, then the gain is almost proportional to 1 over R1. And so it doesn't matter too much. Either one will work. The trim pot, though, adds quite a lot of capacitance. The feedback will kill you. So it may be that the system works with a fixed resistor but doesn't work with a trim pot. But maybe it works with a trim pot here and not here.
Why is the trim pot have capacitance?
Oh, because it's just a big mechanical thing sitting on the whiteboard. And everything has a capacitance. You have a capacitance. Your capacitance in free space, don't do this, it's hard on the ears. Your capacitance in free space is, depending on the surface area of your body, is about 100 picofarads.
So if you put trim pot in there, it's like putting capacitor in a resistor. Is that what you're saying?
Yes, that there are spurious capacitances that go where you don't expect to ground. Clearly, if in real life, if you minimize the physical length of this wire, you help the feedback stability quite a lot. So you minimize the length of the positive node. You keep the output away from the positive node. And, yes, one other very important thing which I haven't said, but I should say, is that for high gain situations, you may well need to put a capacitance between ground and VCC. It's called a bypass capacitor, to absorb small spikes of current. Why would that happen? Well, let's say that you have high gain here. You're slewing this waveform from very positive to very negative fairly quickly. That means that there must be some fairly large currents flowing. Currents flowing this way, then currents flowing this way. If you have large currents changing direction quickly, then di dt is big. That's what we mean, right? Di dt is big. But if there's a little bit of wire, let's say you have a foot of wire going back to the power supply, back to the actual physical power supply. That foot of wire is an inductor. Not very big, a few nanohenries, nonetheless. If you coil it around your finger, it suddenly goes to microhenries. But let's say it's just laid in a tangle on the table. You have a few microhenries. L di dt represents a voltage change. And for fairly moderate currents, you could expect a voltage change here of a few dozen millivolts or maybe even a half a volt. So, changing the output changes the voltage. Uh-oh, changing the voltage changes the output. And now you have another feedback loop, which can cause the system to oscillate. The conservative thing to do in all labs, in everything you build for the rest of your lives, is to put a 0.1 microfarad capacitor across the power terminals of every single integrated circuit you put anywhere. Have you been burned by this?
Not personally.
Not personally, but you know this is a design rule.
Yeah, just like almost every dash from every part.
It says put 0.1 microfarad across it. Believe it, because it'll usually work, but when it doesn't, it's really painful. Okay, so that's kind of the first part of the introduction to general op amps. It's talking about gain bandwidth product. Real op amps have a few other parameters you have to worry about. Real op amps do in fact take a little bit of current to bias them, and you do have to worry about that. That's another reason for limiting this resistor to no bigger than 1 mega ohm, because the bias current for the 358 is on the order of nanoamps. You're generating a few dozen millivolts. It should be able to bias it through 1 mega ohm. Another reason to limit to 1 mega ohm here is thermal noise. The noise a resistor produces is proportional to, so the noise voltage is equal to RT, the gas constant times the absolute temperature times the resistance times something else. Bandwidth. So the higher the resistance is, the more the noise increases as the square root of the resistance. And at some point, the noise produced by the resistance will dominate the output. At a mega ohm, I don't think you're going to see the effect. I think that if you calculate this out for real resistors, at a mega ohm, you're going to get something like 100 nanovolts. By the time you get up to a gigaohm, 1,000 times higher, now you have some worries for real instrumentation systems. Single cell recordings are often limited by thermal noise, but typically not the instrumentation we're interested in. The instrumentation we're interested in this class is going to be normally limited by interference noise from 110 volts, body motion, sometimes RF interference from Wi-Fi. I know one guy who can't have a 3G phone next to his physiology rig because every time the cell phone pings the network, which is about once a second, produces a big noise burst on his physiology recordings. Okay, let's start more on op amps next time.